I swear I sent you one. I remember seeing the notification. Yeah, I did send it. I sent it 2 days ago. It's great. So let's get started. So today we are going to do two things. I'm going to do a compressed lecture on graph embeddings, which will feel a little bit out of place. This would be better after we talk about the other graph stuff. But because I'll do it a compressed version of it, I think it should be fine. It's compressed because partially because I added that impromptu other lecture on like the science of machine learning. So the second thing we're going to do is we're going to do an ethics assessment practice. And so we'll have some activity we'll do in class. And so we'll break you down in groups or in the so breakout room for the people join on Zoom if there's more than 2 people. So we'll do that for most of the lecture. So the context of that is that, let's see, your final project is final report's due in a week. Okay, hopefully you guys have been working on it. I know a lot, everyone had really good progress at their intermediate reports. So I know you guys are within range of finishing your projects, which is good. You can finish up the one for my class and then worry about the stuff for your other classes. So the final report should be 4 pages per person in the group. So it should scale. So if your group is smaller, it's fewer pages. And remember to refer to the project description document for what should go in the report. Yeah, so I think it should be kind of, if you hit the main points in there, with the reports, I will say I usually don't give automatic full points for everyone who completes the report. I like to leave some room. There are some groups that always go a bit above and beyond. So I like to receive, so think of, I think 40, I'll aim for the median to be around 45 out of 50 grades on the report. So don't worry too much about it. And it's unusual to get grades below 40 on the report if you completed everything. If you kind of just barely did everything, you might get like a 40, right? So somewhere in that range. So the rest of the project, basically, if you complete what you're supposed to complete, you get all the credit. Okay, so it's kind of 90 out of 100 is for reaching kind of the minimum I'm asking you all to do. Question. There's 4 pages per group member. Per group member in in the final report. So if you have more group members, I expect a little bit more content. That makes sense. So you do not have to fill all those pages, but I do not want a 100-page report. People have threatened to turn those into me before, and then I'm going to read all the reports, right? And so I want to read them and be able to assess them. And if you send it too long, I'm not going to be able to do it. If you can explain everything in less pages, that's also fine. But don't send me, you can put more in the appendix, but I probably will not read the appendix. Great, yeah. I will read all of them. So if I have fewer pages to read, that you convey all the information, that's good. Okay, but yeah. Was there another question?
Oh no, you can.
Okay, great. One of the things that should go in your report, and this may take up a page of your report or so, I mean, it doesn't need to be. You can choose how much depth to put in each section. Will be an ethics evaluation of what you've done. This is something I've been meaning to add into the class for a while, and we kind of touched on these things, but actually you're going to be this will be a required component of your report. And so what is this? I want you to do the project and kind of explore it and use it as a sandbox to explore techniques. But in the past, I've had projects turn in where I'm like, oh my gosh, I feel kind of uncomfortable that someone did this for a class project with this sort of data. and so generally in the data science degree and other things, we want you to be kind of trained to evaluate the ethical kind of issues that might arise with stuff that you do. We're not going to specify this is right and this is wrong. That's for you to decide, but we want you to be cognizant of these things.
I was just wondering if you give an example. Was it something like the Netflix contest you talked about last time?
I think the Netflix stuff, it's in the realm of like there was some good and there was some bad, and like I think the overall good was better than like the overall bad with the Netflix. It developed like a lot of great machinery, and probably wasn't that much important privacy information leaked in how we would think about it now as opposed to what was like 20 years ago. There was someone who was, one memorable one was someone was trying to build a representation of faces from different, they were trying to assess if someone's face was more Mormon or not Mormon. Okay. And I'm like, I talked them out of doing this. Okay. And I said, and they managed to get faces from Utah and from Washington State, and to do something similar using kind of an eigen decomposition of the face matrix, and still felt a little bit uncomfortable that they were doing this. And, you know, there have been companies that have done stuff like this. So I mean it, but like, I want you to just reflect on these issues. Okay. It's not my place to say that's right or that's wrong, but that's one that I felt kind of uncomfortable was happening, right? There are other ones where this could have been as well, but they're kind of more, the issue is more involved, right? So, okay, great. So we're going to give you kind of a practice on doing that today in class. We're going to do a class sort of activity, and then we'll kind of, you'll do some exploration, and then we'll discuss, and I'll try and give you some feedback. Although I assume just getting a sense and talking it out together, you will probably get some good ideas, and just hearing what other people did is a great way to learn about how to do this. How many people have taken the ethics and data science class or one of the ethics classes? Yeah. So it's okay. So if you've done this, it'll be kind of a similar sort of activity for doing that. But if you haven't done that, it's probably good to kind of get some practice in thinking about these things. Great. So let me get into the graph embeddings. And so the ethics assessment we're going to do is we're going to think about the potential implications of these embeddings. And I want to talk about, we're moving into the graph section on class. So I want to talk about these graph embeddings. Okay. And so the idea is our data now is going to be a graph. And a graph will be composed of vertices and edges. These are the vertices, and these are the the edges. And so you can think of having the vertices as points. Okay, and then you're going to be connecting these vertices with these edges. Okay, so hopefully we talked about graphs before in this class. And so, okay, this is an example graph. Okay, so the vertices can model various things from web pages. Okay, we'll talk about how search engines were built. The Google search engine was built on the idea of thinking about the web pages as a graph. They can be people. Okay, when the vertices are people, you could think of this as like a social network, right? And so social network could be like an online social network, like Facebook, who you follow and who follows you on Facebook. And we'll talk about communities in the next couple lectures on how you can model this in this way. It could also be who you come into contact with, right? When we're all thinking about COVID and who we were exposed to. Were you exposed to someone who had COVID? You would model this as a graph. Did you have a contact or some sort of exposure with someone, right? So there are various other things these vertices can model. Could be some. some companies. Okay, these could be some products. You can think of this as products on Amazon that are linked to each other. Okay, and then the edges define some way of building the connections between them. Okay, and when I model something as a graph, I typically say, okay, there's a connection, or there's there's not a connection, right? So either there's a connection or there isn't. So it's kind of a binary notion. We've also talked about in class that I could define a similarity. So I can define a similarity function between two vertices or two objects, and this will represent the edge between objects 1 and 2, so it can measure some sort of similarity between them, and this can be a value between 0 and 1. So it's not always obvious if you have a connection. There was with COVID at some point, I remember, say if you're within kind of 6 feet of someone, then you had exposure, right? But like, well, does that 6 feet really mean the same thing if you're wearing a mask or not? Are you inside or outside? Were you in a well-ventilated space or not? And there's all sorts of ways of modeling this. And the same way with social networks and web pages. These edges can have strengths. You could think of them as having some sort of direction. This person follows this person, or vice versa. In most of the modeling, in a lot of the modeling in graphs, the direction matters, but not as much as you would think. Okay, keeping track of the direction of edges is sometimes kind of complicated. It tends a lot of the analysis will end up doing if you make all edges bidirectional, the results usually turn out about the same. That may be different with the PageRank models in some cases, but in most cases it doesn't matter too much. Sometimes it'll matter a lot. Okay, so we're given these graphs. It can model data in a variety of ways. And so what we want to talk about is how to embed the graphs. What this lecture is about is I want to draw the graphs. So a graph embedding, okay, is a mapping from a graph, okay, to where the vertices are going to be in RD, okay, and where some notion of the distance between nodes V1 and V2 is somehow a function of the edges in the graph. Okay, and there are different ways of doing this, and we're going to kind of talk through some various ways. Why is this interesting? So, I mean, in this picture, I already had my graph drawing in 2 dimensions here. I drew all the vertices and I connected them by edges. Seems pretty reasonable. Like, why do I care about the graph embeddings? Is because the input data, the input is usually given in where I just have a list of vertices. So V is V1, V2, and each vertex will have some, it has a pointer to all the information about it, right? And I also have a list of the edges. So E1 might be a pair V1 and V7. E2 is just between V2 and V3, and ... So my input will just be the list of the vertices and the edges. It will not give me the embedding. And so I would like to be able to embed it when I have the embedding. If D is equal to 2, for D is equal to 2, then I can draw a picture. Okay, If D is equal to some K, and I can trust the distance after the embedding, I can do things like clustering, or, you know, I can apply my classification. Okay, and so there's a bunch of things called these graph neural networks. They're basically ways that are trying to embed graphs into these high-dimensional spaces, and then classification works once I build this embedding. Okay, so it's hard doing classification directly on the input of the graph is harder to do, but once I have the embedding, I can use all the machinery you will learn in the machine learning class. So the real hard part is, how do I get this embedding into RD so that the distance between the vertices sort of makes sense as whatever the edges are supposed to be. Okay. And there are a bunch of modeling, kind of because what the edges mean is a bunch of modeling, right? Maybe it's a binary notion, maybe it's some sort of similarity function that I could think of as an edge, if it's above a threshold, or, you know, I can put some weights on the edge in some way. Great. So, okay, so what are, let's kind of just pretty quickly, because I want to move on to the other activity, but this sort of modeling will be, well, thinking about modeling and ethical situations in graph embeddings and whatever they can represent here. But let me give some examples of how to define graph embeddings. And it's mostly ideas you've seen before in class. We can use multidimensional scaling, where I have the, this took as input a set of vertices and then a distance function, right? Well, V1, V2, right? So I can define a distance function. And one way of defining this is that the distance is 0 if there's an edge, E, V1, V2, in my set of edges, and is 1 and 1 otherwise, right? So I want them to be close if they have an edge between them. So kind of usually you would model an edge as 1 if it's there and 0 if it's not in an adjacency matrix. But the other is to say it's close, it's this and 0 if they have an edge, and 1 if they don't have an edge. Okay, so I could use this. This is not commonly used. Commonly used. It's kind of blunt. Okay, and so if I go back to an example graph and two vertices are 1 hop away but not directly connected by an edge in a really big graph, they should be kind of close to each other, but if they don't have an edge, then I don't model them as close, right? So I can just, this would be the same as inverting this similarity function 1 minus the similarity function I could use here. And this is not the most commonly thing used. It's because it kind of, if you have a binary representation of the edges, it's kind of too blunt of a measure. I want to understand something more universal global about the edge set that says something more interesting about this. But if you remember what the idea was here, this idea is going to kind of hold the secret that almost everything is trying to do, is I'm going to build a matrix D squared, right? Which is going to be this is an element of the size of the vertex set by size of vertex set, so a square matrix, and it's where the D2 ij is going to be kind of, again, this distance between V1, V2 as defined above here squared. And then I basically am taking the eigen decomposition of this. So I do the eigen decomposition of the D squared matrix, maybe after doing centering. And so this will give me some eigen vectors, say U1, U2, ... And I just project, or I can read the data off of these So I can just use the embedding. So let's say phi of v into rk would be equal to u1, the index, this is vi, index I, u2, index I, up to uk, index I. So I can just use the eigenvectors, take the top k of them, which captures the most variation, and this gives me the embedding. This is just a reminder of what multidimensional scaling was doing. It probably is also scaling by the eigenvalues. Okay, that tells me how much to scale them out. Okay, so this sort of idea of creating this distance matrix, or kind of I think I need to do the centering in here. I'm misremembering. I need to do the centering matrix inside of here because I want to use the similarities instead of the distances here. Okay, but I want to take the similarities and do the eigendecomposition of this, and then I can use the top k eigenvectors to tell me how to embed this into a k-dimensional space. So if k is 2, I just read off the coordinates from here. Okay, so this is kind of the basic idea I would like to do, but there are different ways of how do I define the matrix that I'm going to use in order to get what the similarities I'm projecting. The other thing we've talked about before were the Laplacian matrices. Okay, and now this has 2 components to it. Now I'm going to let D be a diagonal matrix of the degrees. Okay, so this will be the degree of vertex 1, the degree of vertex 2, and the rest are going to be zeros. Degree of vertex n. And then A is going to be the adjacency matrix, where Aij equals 1 if edge Eij is an edge set and is 0 otherwise. Okay, so we talked a little bit about the diagonal adjacency matrix when we talked about spectral clustering, right? And so then I can define the Laplacian, the unnormalized Laplacian as D minus A, or I can define the normalized Laplacian as the identity minus, and I'm just writing this up quickly because this should be in your notes from spectral clustering, minus 1/2, right? So I do this D to the minus 1/2 times A times D, I minus this. This kind of normalizes by the degrees inside of the matrix. And I get these n by n Laplacian matrices. And again, we had used these to take the top eigenvector, and then we found the best split for spectral clustering by projecting stuff on the top eigenvector. And we were trying to minimize what the normalized cuts were. But instead, I could take the top k vectors from the top k eigenvectors of the Laplacian matrices, and I can use this to embed my graph. Okay, and so this does a pretty good job of separating things, kind of spread things out so that if something has a small or a small normalized cut, meaning that I don't cut too many edges and I have balance on either side, it will kind of project them in this way. And this is one way to do some sort of graph embedding. The normalized Laplacian, the second one, will do a bit better with the normalized cut, but the first Laplacian is also used in some cases. Okay. This actually works pretty well, and this is probably the first thing I would suggest to try and do if you want to do graph embedding. If n, the number of vertices, is say less than 1 million, okay, so let's not say, maybe that's too ambitious. Let's say less than the number of nodes is less than 10,000. You're probably not going to do better than using just one of the Laplacian matrices to embed your graph. Okay, you're probably not going to do much better than this. It's not the fancy thing that everyone's using, but it works just fine. This one, to compute the eigen decomposition of this matrix L when it's 10,000 by 10,000 is totally doable on your laptop. Okay, probably 100,000, you can probably do it. Okay, and if you need a bigger computer, you can probably do it. Okay, if you have even larger number of vertices. Okay, there are methods we'll talk about next that can scale up even larger, and these are what, if you look up graph embeddings on the internet, they'll tell you about these more complicated approaches. But if your graph is reasonably sized, you can just use this and it'll just work. Yeah, so just do the embedding with this. Yeah. So once you get, okay, the key here, the part that you're getting as the outcome is you're going to get some square matrix that's capturing the similarity between the vertices of the graph, somehow based on the edges. This one is just directly looking at if the edge exists or not, or maybe directly looking at a similarity function. This one is computing this Laplacian information, which tells you something, maybe tells you something about like random walks a little bit. And for some sense, that's true. We'll talk more about random walks in the next couple lectures, so I don't want to go into it too much. But it's kind of telling you something about if you randomly walked on the graph, how frequently are you likely to get from one node to the next? Okay. We'll go much more into detail in this model. But you're getting the square matrix, and then to get the embedding, you do the eigen decomposition. You take the top k kind of eigenvector embedding. Okay, that's all these embeddings are really want to be doing. There are other ways you can try and learn embeddings, but most commonly they want to, preserve the most variation in the graph, and in this case, it's preserving kind of this. This is directly associated with the normalized cut. It's kind of the best way to kind of choose a set of directions that capture the normalized cut information. So for very large scale k-means clustering, one approach people actually use in practice is they'll try and approximate the Laplacian matrices to get an embedding, and then they'll run k-means clustering on the embedding. Once they build a sparse representation of a graph of the data from really high dimensional or abstract spaces. So, but you can just use it as the embedding to kind of visualize what's going on as well. Okay, so kind of this is kind of the first thing you should probably try to get an embedding. What is more common are these graph neural network-based approaches. And graph neural network can mean a couple of different things. I think it's used a couple ways in the literature. But what this is talking about is to learn an embedding from a graph to a phi of. So I'm trying to learn an embedding from the graph. So the vertices are in RK. For some Euclidean space, as they're represented as vectors, it's kind of the layer of a neural network that I pass the graph into the information about the graph in the neural network. And at some point, every vertex is passed through and is represented some layer that's k dimensions, and that's what this representation is. Yeah. So let me explain kind of at a high level what these are doing, and they're actually the techniques I will be doing in particular, and there's other things that people call graph neural networks, but I'm talking about what's in these famous papers from DeepWalk and Notivec. Okay, what these are doing, what this is, they're kind of approximating the Laplacian. Okay, they're weighting stuff a little bit differently, but from a 10,000-foot view, they're basically approximating the eigenvector embedding of the Laplacian is what they're doing. Okay, so does it need to be deep to do this? Probably not. Okay, so let me kind of explain what these are doing, and I'm not going to kind of derive what the connection is to the Laplacian, but there's a way to see this as kind of approximating something like a Laplacian, and I don't think it needs to be very deep to do this. It's just trying to learn something based on the graph. Okay, so what's going on is that they have some graph, and their edges. Okay. Okay, it does not need to be a planar graph. And then what's happened is they want to model what's going on when there's an object which is taking a random walk on this graph. Okay, right? So I'm taking a random walk. So, okay, so I could start here, and my random walk might look like this. Okay, so this is the random walk on the graph. And so then I want to analyze some vertex, call this as vertex V, and let's look at all of the random, and let's look at a link, or let's call this a neighborhood length. Okay, and I'll call this L. And so in this case, we'll say L is equal to 2. So I'm going to look at all the paths of a potential random walk, okay, let me draw these a little thicker, that go through this vertex. Okay. And so the random walk can be much longer. Okay, but I want to look at ones that start someplace, go 2 steps, hit this vertex, and then go 2 more steps. Okay, and then everything that is intersected by one of these walks, this is called the neighborhood. So these are for the neighborhood of a vertex V given a kind of a path, right? So this would be one path here. So this would be a path, right? This is going to be this is a subset of all of the vertices, right? So this is for one of the vertex VI. I have a path that goes of length 2 before it hits the vertex and 2 afterwards. And so then I want to say, what are all the vertices in the neighborhood? And now I want to say that the similarity between vertex I and vertex J is equal to the sum similarity function between the kind of the union of all paths of the neighborhood of VI path and the union of all paths of the neighborhood of Vj path. Okay, it's some function that says they're similar if their neighborhoods from the paths are similar. Okay, so that could mean kind of two things. One, this vertex should be next to its neighbor because the neighboring ones are probably going to have a lot of similarity in the paths. That they're near the other things, right? So vertices that are connected to it are probably fairly similar. Okay, this is probably makes sense in the graph. It could also be that I have something where I have a graph that looks like this, right? Where there are two vertices here, Vi and Vj, that all paths that go through these kind of go through the same stuff, even though they aren't directly connected to each other, but the neighborhoods kind of look similar because all of the paths through here could either go here or this way. And so the paths all look similar to each other, right? So these vertices could be replaced. One could be replaced by the other one. Okay. Okay. And so this kind of, I want to define a similarity like this. That's what these graph neural networks want to do. And there's a way to how they define the similarity. If you do this the right way, and similar to what is most commonly done, then the similarity actually looks like the similarity I get out of the Laplacian. Okay, so it's pretty similar. So I want to then, I could build up the similarity by taking lots of random walks, looking at all the neighborhood groups, and then computing a big n by n matrix of the similarities between. This is for a really big graph. That's a bad idea, would take way too long. Yeah. Yeah. So I'm thinking, right, I'm thinking of the paths from random walks.
Okay.
So this is yeah, well, I can generate more random walks to generate more paths. Right. So I do lots and lots of random walks. We will, yeah, not just one. Yeah. So in practice, this will be the last thing I say about it. In practice, this is scalable because I can optimize the embedding with stochastic gradient descent. Okay, so I want the dot product. I want the goal is that the inner product between phi of Vi and phi of Vj to be approximately this similarity between the neighborhood of Vi and the neighborhood of Vj, defined based on, in the limit, based on infinite number of random walks and infinite number of these possible neighborhoods. So if I were to take the random walks to the limit and get arbitrary many of these, this will kind of converge to some distribution, and I can measure the similarity, think of the similarity there, and I want to approximate that. And I can do that with stochastic gradient descent. I can be running a random walk on the graph, and every chunk of the random walk of length 2L tells me, well, the middle vertex, I get an observation. And I look at the similarity between that vertex and other ones, and I update its neighborhood. Okay, and I can optimize this without computing the whole similarity matrix. And so you can, on huge scale graphs, you can do this faster than doing the eigendecomposition. Okay, and so these work on these really big scale graphs. But if your graph is not that big that you don't need to do this, you're better off just using the Laplacian. It's not entirely true. Some of the advanced versions of these have better modeling that you can put in that might be harder to think of in the Laplacian. You want to weight certain vertices more than others in various ways, and maybe you can control that better with this approach. But in general, the Laplacian is a great first approach here. All right. So it's hopefully just mostly demystifying what a lot of this stuff is doing without getting into all of the detail of like DeepWalk and Notepad. But if you want to use those, it's kind of what it's doing under the hood. All right. All right. Okay. I want to break and switch to this ethics kind of activity. And so what we're going to do here is I'm going to, and let's get, you're going to, yeah, let me first show you kind of the first thing we're going to do is we're going to be looking at this demo for word vector embeddings, just to give you a better sense of what these embeddings can model. This is, at some point, my research group helped build one of these, but it's harder. This one just kind of works online. It's a little bit clunky, but you can kind of play with it. It's embedded a bunch of words here. And so all the words that it shows are, this is from probably like a word-to-vec embedding. I don't know which one. You can add other words, like what's a word you'd like to add? Let's say data, okay? And okay, it's added the word data into here, and it's off to the side someplace, okay? It can also, it defines, just to help you navigate this, it defines two axes, gender and age. And as you can see, the gender encodes the female, definitely female words, mother, girl, princess on one side, and the male words on the other side. And for age, it has the younger, girl, boy, prince, princess on the bottom, and mother, man, king, queen on the top. So it's encoding age in these two axes. This is an actual kind of dimensions that exist within the embedding. It has one other dimension that they call the residual, which I think is the top principal component of all the other vectors. So it's the best one-dimensional thing of everything else. Okay, and then you can define your own axis, and you can do it by putting in a bunch of words here. These are the words that define the gender axis, and you can define your own one. Before you do that, you have to enter the words here. So if I want to define a word that has to do with, so for instance, they have one that is about capitals. It has Texas, California. The capitals are Austin, Sacramento. I have to input those words in this box first in order to do it. So it's a little bit clunky to use, but it works reasonably well, and it's robust online. Okay, yeah, question.
The way that
yeah, it's kind of I would call this a kind of it's doing, yeah, so it is dimensionality into 3D. It's not just doing principal component analysis. It's picking the first two axes. They are defined by taking the embedding of all these words that are male, taking the embedding of all the words that are female, taking the mean of both of those sets of words, and looking at the one-dimensional vector that spans those means, okay? And then use that as, make a unit vector out of that, and that defines one of the axes. Then do that for another one that defines age. See, these are the words that define age. Learn that vector. This defines the second axis. And then the third one, they project those, at least this is how we implement it when we had our version of this. We projected those two out, and then we took the principal component of everything that's left to get the third axis. All right, so it is dimensionality reduction, but it's this directed way. Yeah. Yeah, so you get, the point of this is you get to pick the axes to kind of visualize this pattern. I can put in something that potentially, let's see what happens in here. I put in the word doctor, and let's see where this shows up on the gender axis. It looks a little bit more male on the, should not be too surprising. The word doctor, it's a little clunky here. The word doctor is a bit more on the male side. It's pretty neutral, in fact. but there are certain like traditionally male professions, or maybe doctor isn't even traditionally male anymore, but certain ones which will stereotypically be embedded on the male side. Okay, and this at least the original Word2Vec and glove embeddings, they had this at some of the papers that kind of were demonstrating these things. And so you could sometimes find these, but they're not always as obvious as you would think they are. But there are some words in here. So I'm going to have you. So I'm going to pass this around. Each of you are going to work on this project in groups. Take over if you want. Take over one of the screens if you want to. And so the first thing I want you to do is to play with this. You could also gather around a laptop if you want to, but it's to kind of play with these embeddings. The link for this can be found off of the class webpage today, and find some sort of relationship that you think is interesting. And then I want you to conceptually think through. There'll be a bunch of prompts, and we'll gather for the last 5 minutes or so and discuss what each of you came up with. So let me send it out to people on Zoom. All right, you guys can take over these things, and then I will send it out on Zoom.
Yeah, sure.
Hey, everyone on Zoom, let me try and put the worksheet in the chat. Since there's only 6 of you on Zoom today, I'm going to, where's my chat? I'm going to try and I'm going to try and paste. Hold on, it's not letting me. I'll paste the worksheet, and you guys can work on it together and turn it all in. So this makes sense to everyone on Zoom. You guys can work together. I'm going to turn off screen sharing.